Okay, I want to look at the remaining two gates. We have looked at quite a few. Started off with the NOT, went to the AND, the NAND, and then went to the O. And lastly, we did the NO. Now we're going to try to look. Remember, I said the O and the NO, those were inclusive because they were otherwise including, they were otherwise including states that were not necessarily O or no. So what we're going to look at now is what the exclusive no, which will only allow a what? An or state or a no state. So let's look at alright, this gate is a little bit we will see later when we look at it practically, maybe when we build a sketch together, you'll see how it's so complex. I'm not going to try to draw this circuit here now. So about 5 transistors, a couple of switches, and indicator LEDs, and the output LED and stuff. Is a little bit complex for it to be easier to look at it when you're looking at when you're looking at maybe practically, when you're looking at it practically. So for now, I'll exclude that. I'll jump the what? I'll skip the circuit for it, the actual circuit for it. What I'll do is the representative circuit, which is the switch equivalent circuit. So let's say we are looking at the what? The exclusive OR. We are still with logic gates. And we're going to look at what? The exclusive OR for a change. We've looked, remember what was our issue with the OR? Our OR was, let's have 2 inputs. We know the combinations now: 0, 1, 2, and 3. There's only 4. Why? 2 to the power of 2 inputs gives us 4 of these combinations, and then our output depends on them. Now, with the OR, we had, as long as there was a 1, we looked out for a 1. So now, unfortunately, this is an end state. So the exclusive OR gate does not allow this end state. It stays with the what? With the exclusive OR scenario, right? So it means only OR is allowed. So this is what? This is our truth table for the what? For the exclusive OR gate. Obviously, the exclusive NOR is otherwise the NOR gate, which was 0, 0, 0, 2 input NOR, 1, 0, and 1, 1. With the NOR, remember OR and NOR look out for what? Look out for what call these ones. But with the OR, it would have been a 0. With the NOR, it becomes a what? With the OR, it would have been a 1. I mean to say, with the NOR, it's a 0, as long as there's a 1. Where there's no 1, you then get your what? Your output. So it's looking out for ones. With the case of the OR, you would have a situation where you what? With the case of the OR, you'd have a situation where every time you say a 1, your output follows suit. But exclusive OR does not allow the end state. So even here, the end state will not behave like the other states. The end state will, in fact, be unacceptable. All right. Remember, it was unacceptable here, but it will be acceptable for the what? For the no. If you look at the OR and the no, the exclusive OR and the exclusive no, the 0 here is actually a 1 there for the same state: 0, 0. 0, 1, that one is a 1. Obviously, these are opposites. As you can see, this is the entire opposite of that. Now that we've done complements, you will say this is actually what? This is actually one's complement. Exclusive no is one's complement of what? Of the exclusive, or in fact, it's the inverse of one what? I didn't say this is our output. So as you can see, these two are opposites. Now, symbol wise, the exclusive OR, our input is A and B. Remember that it should have been A or B, but we say only that state is acceptable. Okay, here we say A or B. This, I'm saying or B, but all right, A or B. These are all gates, but only that state. Okay, so our output for the exclusive OR is that. Our output for the exclusive NOR is not the exclusive OR, it is the opposite. of the exclusive no. I don't know. But then also, if you look at this state here, this is not A. A is not on. This is not A, not B. So this is not A. Okay, I won't come here. I will say I will only worry about where I've got outputs. Here is not A with a B, but here is A, but it's not B. So if I get an output through this situation or the other situation, so our output is also not A, B. If I combine not A with B, or I combine B with not A, no, so what am I saying? Or I combine A with not B, remember this A, this B, or I combine A with not B. That is, so our Boolean equation for this guy is either the top or the bottom. Okay, this is our Boolean equation, all right? But if you look at the other one, we get an output here where we have not A combined with not B gives us an output, or A combined with B. So our output here can also be expressed as what? As, so this means the same as that. And this means the same as not A combined with not B, or A combined with B. This is when we get output. We get an output when you combine not A with not B, or what? A and B. I don't know if that is complex. I'm hoping not. So let's look at the circuit. All right, basically so far we've been looking at switches. We've been talking about what of switch equivalent circuits. The circuits we've dealt with so far, the switches we've dealt with so far, we've been what you call a one pole, one line going in single pole. But the switch is also throwing one way, so one pole. So this is single pole, single throw switch. Okay, single pole, one line came in, that one line threw away one line. Okay, one line come in and one line went out. So it's a single pole. Now let's introduce a different type of switch, and we're going to call it one line comes in, so it's one pole, but it can throw that way, or it can switch to the other side. And this here is called what? This is, it can throw that way or that way. What did I say here? I said one pole, one throw, but I still wrote 1P. That is supposed to be one throw. Single pole, single throw. And this one is single pole, one line came in, but that line is able to throw two ways. So this is called two throw. So this is a single pole. Oh, what am I doing? Single pole, double throw. So if you use a single pole double throw switch, we can actually come up with our exclusive or an exclusive no. Let's try and see. If we had, let's suppose we had two of these switches. Common is our single pole is throwing either that way or the other way. And let's call that switch A. And it's facing another one pole in, two ways to leave. So it's a double throw. So it can either go that way or this way. That way or this way. So this is the common point here, right? This is, we're going to call this our B switch. So there's two ways of what? Of connecting these switches. Okay, either we connect through an equal sign, that is equal sign, so that, why am I saying equal sign? We know that's our equals. So we either connect through our equal sign or through our time sign. If we then look at the other alternative, is we can connect, I'm trying to what? To have straight lines there. All right. So now, either we're going to have, I'm using a pad, and pads are not easy to actually achieve some of these things here. So either we can connect this way, or we can connect equals. Why am I calling it equals? Because there's equal signs like that, our time sign is like that. Now, if we connect through an X times, this is gonna be easy to remember. That is our XO connection. If we connect through the equals, that is our XNOR connection. So now let's take this switch and put it in a circuit. In the ones case, I will connect, so there are my two switches, throwing that way or that, and the other one, switch B, which also throws the one way or the other way. Okay, in our first case, what I'll do is I'll supply this to a load, and I'll come back and close the circuit. Right now, so I have two ways to connect. Remember, I either can what? Do the equals, or I can do the what? I can do the X. Let's start with the what? With the X. I want to change this. It's rotating. I want to start with the X. I can get rid of them in one swoop. Okay. Now, let's start with the X. Let's say I connect them exclusive OR. Remember, X for exclusive OR. Okay. Now, if we are going to call this the higher end, I mean it's above these two ends here. Those two ends are above those two ends. So let's just call them 1, just to make our life easy. Let's be constant. The upper ends, let's call them 1. The lower ends, let's call them zeros. Right. So that we've got switch A and switch B. Now our switch A and switch B, if you look at this, our supply, this is our output, the load Z. Let's say now our switches are on condition. Let's just say it's still two switches, but what am I doing? Still two switches, 0, 0, 1, 1, 0, and 1, 1. Now if we look at this, our output Z, if these two switches are on what? Are on 0, 0. Now, what we mean is that will not be there. Instead, the connection will be 0 and 0. Remember, in electronics, in electrical generally, we no longer use these two mean lines are crossing. Okay, if two lines are written like that, there is no connection unless you bump them up like that. This means they are connected. So these two lines here are not connected. If we now analyze this circuit here from the positive, we come to the common of A, we go there to 0, we end up hanging there by what? By 1. So there's no continuous path. If I came through the negative, I'll still come through Z, come through 0, go to 1 and hang. Since there's no connection there, this circuit is actually discontinuous. So the circuit is broken. So if they are both at 0, our output is 0. Okay. Now, if we then have the second one, if we then have the second switch on a what? On a high, now you can see that our circuit is closed, and therefore power will go through our output and our output will go on. Alright. Same as if we then decided that no, we will take our first switch high and our second switch low. As you can see, our circuit is continuous and therefore Z is getting power. However, the final scenario is if we are to then put them both high, okay, what's happening here? It's breaking there, and if you follow the other path, it would have been, they both break at 0. There's no continuity. So what happens here? Remember again, there's no what? A dot there would have meant there's a connection. There's no dot, so there's no connection. So what does it mean? The circuit is open. So this here is what? If you come and look there, X stands for exclusive OR. There is our circuit. 0 0 gives us nothing. 0 1 when we have the OR condition exclusively, A yes, not B, it would have been AND, or B yes, not A, it would have been AND. We reject NAND, we reject AND, we reject NAND. So this does not include any other state except the O. So this is our exclusive OR truth table, but I'm just proving that the circuit would have been. How do you remember it? With X stands for exclusive OR. The X stands for exclusive OR. Another thing that you have to note here, you get an output when the two inputs are not equal. So we sometimes call this the inequality comparator. So it compares the inputs, and when the inputs are not equal, you actually get a what? An output. Alright. So the exclusive OR is also sometimes called the what? The inequality comparator. This is one way of wiring the what? The two switches. We could have decided these are not equal. If you look, this is an inequality comparator. The 1 is connected to the 0. The 0 is connected to the 1. Okay, so they are not equal. It's the inequality comparator. Now, if we take the same circuit, 0 0 0 1 1 0 1 1, but what do? We make the connections equal. With what? With the equal sign. There is my equal sign connecting the what? So it's not difficult to actually remember this, because what? Because the equal sign will obviously give us the equality comparator. It will compare, and when they are equal, it will be happy. Let's see. Now they are already equal, they're on 1, and you see you are getting what? You are getting a continuous circuit. So when the two are equal on high, you get a what? You're happy. Now you say, okay, what about if I make them equal but down, not up? So I make them equal but down, not up. What happens here is there is again continuity. Our output is going to be happy. Our output Z is going to be happy. However, if you decide that you don't like the equal sign and you make them unequal, now one is on the low, the other is on the high. One is on 0, the other is on what? Is on 1, and you can see that what? So this is A on 0 and B on 1, and you can see there is no continuity. There can be no power for the what? On the light. If you also did the other inequality, which would be to make A high but B low, you can see that gap there. Okay, it does not like when there's no equality. It's an equality comparator. They are unequal, and it says no sir, no thank you. So as you can see, this is a what? The one with the X is my switch equivalent circuit for the what? For the exclusive OR. The X for the what? The X for the exclusive OR. The equal for the what? The equal for the exclusive NOR. As you can see, the two are actually what? inverses of each other. The two are actually opposites of each other. This is our what? These two are our what call this? Let me rather do this in summary. Let me take this part together with, no, let me take it alone and move it a little bit up. What am I doing? Yes. It's supposed to move up. No. Okay. Must you hold it in a specific space, because now what I'm gonna do is I'm gonna take that one down, move it a little down, and I'm gonna take that circuit and I'm gonna say we clone you, okay, and then we say, all right, in the one case you are okay, okay, we say in the one case we XU together, we make the input and the what, the connections unequal by doing well, doing what, by actually crossing with the X for exclusive OR. Oh, it's an X, so this is exclusive OR. But then this one here is what, is an equal, so these are what, our exclusive NOR. Right, so this is our what, exclusive NOR. You make it equal. This is the equality comparator. Not equal, this is the inequality comparator. So these are our what, were the two remaining gates. I hope that was a little bit what did we do here? We dealt with the symbols. Did we do the symbol? No, I've not done the symbol. I will come and say, let me first move this. I don't want people to forget my types of switches there. Okay, and I'll move this a little bit to the left. Now I'll say, maybe I need to remind people that the exclusive OR has the X for exclusive OR. And the exclusive NOR is the equals. Is the equality comparator not equal? All right, and then we come and we say, but our symbols, we didn't do our symbols. The symbol for the exclusive OR is simply the inputs must be equal. We don't allow greater than now. The greater than is the one that opened up what, the opened up a multitude of possibilities. And ended up having what, the AND gates. The inclusivity came from the what, from the greater than. Now we say only if the two inputs only one. We are saying all means only one. If I say you or you, I can say it 20 times, but only one as long as I say it all. So this here is our what, is our symbol for the what you call this, inequality comparator. Now the other one, same thing as we've seen with our symbols, except a little zero to say not. And what do we have? Oh, it shouldn't go in. What do we have there? We have got A exclusively or B. All right, it can only be A or B, it can't be both. Okay, so here it can only be A or B, it can't be both. There, if it's A or B, I'm not happy. Okay, this is what basically it means there. It says not or, not exclusively or. So this is our what, our exclusive NOR. So the first one there is our exclusive OR. There is the switch circuit for the exclusive OR. There is the symbol, there is another name for it. Okay, there is the truth table, 2 inputs, only 2 to the power of 2 possibilities, therefore there's 4 possibilities. And then we shouldn't forget that there's what we also have the Boolean equations here. Remember, z is equal to only or a or b, okay, which we said is the same as unequal. If a is high, b must not be high, or if a is not high, b must be high. That is the what? The inequality comparator. Now for the equality comparator, they must both be equal. If a is low, b must be low, or if a is high, b must be high. That for me was a little bit easy, but I hope you also follow and you are happy. Anyway, I've done all the gates. What's left now is for me to do the what? The combinations of gates. Okay, I've done all the gates. Now what we have to do is put some gates together and see if we can analyze and see what possibly a truth table could come out, or what kind of circuit gates that are put together. We could be given a statement, and we could be asked to draw a what do you call this, combinations of gates from it, or we could be asked to derive a truth table. So we'll deal with combinations in our next in our next episode. Thank you. Ciao.